is the clock driven scheduling. So some notations and assumptions before proceeding with the clock driven scheduling. We assume a restricted periodic task model throughout this chapter, otherwise this unit. The following are the restrictive assumptions. First one is there are n periodic tasks in the system. As long as the system stays in an operation mode, n is fixed. The second restrictive assumption. The parameters of all periodic tasks are known a priori. In particular, variations in the inter-release times of jobs in any periodic task are negligibly small. In other words, for all particular purposes, each job in Ti is released pi units of time after the previous job in Ti. The third restrictive assumption, each job Ji, K is ready for execution at its release time Ri, K. We refer to a periodic task Ti with phase phi I, period Pi, execution time Ei and relative deadline Ti by the four tuple phi I, Pi, Ei, Di, capital Di. For example, if I take 1, 10, 3, 6 as a four tuple for a periodic task, then the phase is 1, period is 10, execution time is 3 and the relative deadline it is 6. Therefore, the first job in this task is released and ready at time 1 and must be completed by time 7. The second job is ready at 11 and must be completed by 17 and so on. Each of these jobs executes for at most 3 units of time. The utilization of this task is 3. By default, the phase of each task is 0 and its relative deadline it is equal to its period. So, we will be sometimes omitting the elements of the tuple that have their default values, like we will be omitting phase and sometimes the relative deadlines if their relative deadline is equal to the period. As examples, we can take it like 10, 3, 6 where we are omitting the phase, and in the second example 10, 3 where 3 is the relative deadline. Then the meaning of this is or the period the period in the second example the period is 10 and the execution time it is 3. So the other thing, the deadline it is missing, the relative deadline it is missing. So the meaning of it is the relative deadline it is equal to the period 10. So it would be, if it is given, if the value if it is given, then it would be 10, 3, 10. So that is the thing. That's why we are omitting the last 10. Their relative deadlines are 6 and 10 respectively. Static time-driven schedule. This is the next topic. Whenever the parameters of jobs with hard deadlines are known before the system begins to execute, a straightforward way to ensure that they meet their deadlines is to construct a static schedule of the jobs output. This schedule specifies exactly when jobs execute. According to this schedule, the amount of processor time allocated to every job is equal to its maximum execution time and every job completes by its deadline. During runtime, the scheduler dispatches the jobs according to the schedule. Hence, as long as no job ever overruns, all deadlines are sure limit. So we consider a system that contains 4 independent periodic tasks. They are T1, T2, T3 and T4. Their utilizations are 0.25, 0.36, 0.05 and 0.1. And how we calculate the utilization time is Ei by Pi, where Ei, if we take for T2, Ei is 1.8 and Pi it is 5. And here for T2 it is not like Ei Pi, it is E2 P2, E2 by P2, E for execution, P for period. So their utilization values are given, and the total utilization it is 0.76. It suffices that to construct a static schedule for the first hyper period of the task. Okay, so this total utilization 0.76, it suffices. Since the least common multiple, the LCM of all periods is 20, the length of each hyper period it must be 20. The entire schedule consists of replicated segments of length 20. Figure 5.1 shows such a scheduled segment on one processor. So this is one hyper period. This 20 length of time segment it represents one hyper period during which all the jobs are executing their job slices for once. We see that T1 starts execution at time 0, 4, 9.8, 13.8. So it is starting at 0, 4, 9.8, 13.8. T2 starts execution at 2, 8, 12 and 18 and so on. All tasks meet their deadlines. Some intervals such as 3.8, 4, 5.6 and 10.8, 12 are not used by the periodic tasks. These intervals you can use them for executing aperiodic or sporadic jobs. A straightforward way to implement the scheduler is to store the pre-computed schedule as a table. Each entry in the table tk, capital T of tk gives a decision time tk, which is an instant when a scheduling decision is made, and T, capital T of tk, which is either the name of the task whose job should start at tk or capital I. That I refers to an interval during which the processor is idle and where you can execute the scheduling of a periodic job or a sporadic job. So in the example shown in figure 5.1, the stored table contains 17 entries and they are like 0, T1, 1, T3, 2, T2, 3.8, I. Why means at 3.8 no job is executing. That's why I am using the letter I to indicate an idle interval. Hence the timer is set to expire at 0, 1, 2, 3.8 and so on. We call a periodic static schedule a cyclic schedule. Again, this approach to scheduling hard real-time jobs is called the clock-driven or time-driven approach, because each scheduling decision is made at a specific time, independent of events such as job releases and completions in the system. So this is a example clock-driven scheduler, and the input here is the stored schedule, and the task is scheduling the jobs according to the entries in the stored schedule. So the next topic, it is the general structure of cyclic schedules. The first subtopic, frames and measure cycle. So what is a frame and what is a measure cycle? The scheduling decision times partition the timeline into intervals called frames. Each frame has length f, where f is the frame size. Because scheduling decisions are made only at the beginning of every frame, there is no preemption within each frame. And the following things, these equations, they are the frame size constraints. The first constraint says that the maximum frame size, it must be equal to the maximum execution time among all jobs present in the frame or the hyper period. The second thing states that if the second thing is achieved, then the meaning is you are able to divide the hyper period into integral number of values, integral number of frames. The third thing what it says is it ensures that if you take time t and a later time t dash, then it ensures that t dash is always later than t. Nothing but in this t and t dash we can have any number of frames like 1, 2 or 3 and any other number of frames. By maintaining this third item, the third equation, by achieving this equation, we can ensure that those frames in between the time intervals t and t dash which we are taking, they are compulsorily present within this time frame and they are not exceeding this time frame. So in this example, for the third equation we can take this example where t and t dash, if they are later, then no doubt t plus 2f must be earlier than t dash plus ti. T dash plus di, it is the deadline of t dash. So if t dash plus di is the deadline of t dash, then no doubt frame k and frame k plus 1, they must be given this t dash plus di. Nothing but we can take it like t plus 2f, it is less than t dash plus di. And by implementing such a kind of thing as an equation, that is what we are implementing here is we are implementing by taking the equation t plus 2f less than or equal to t dash plus ti. Then we